Okay, good afternoon. Welcome back to Advanced Modeling Methods. And today we're going to talk about another way of formulating the method of weighted residuals. And so far we've done global collocation, local collocation, and which led to the finite differencing method. And we've done subdomain, which led to the finite volume method. And today we're going to do something called the Galerkin formulation, which at the end you'll notice that it will lead to the finite element method for formulation, the FEM formulation. So it's perfectly equivalent to that. By the way, I'm going to go through the formulation process, and then I'm going to show you a MathCAD file where I actually implemented these. It's a little bit more involved than the previous two because it involves actual integration of the coefficients. But it's the final form is the same level of complexity. It's actually the same dimensions and so on. And I've already posted the assignment, the first project assignment, which is due Thursday of next week, so about 10 days from today. And it involves a very similar project, a very similar problem, a 1D heat conduction problem, which obviously the equation is different, the boundary conditions are different, and you are to implement the finite differencing, finite volume, and finite element method to solve the problem. You're free to use whatever spreadsheet or mathematical spreadsheet you want to use. You can even use the ones that I posted and alter them accordingly. On next class on Thursday, I am going to take everything we've done, and I'm going to translate it into MATLAB. I'm going to do it in class. So you can also use that one. All you have to do is alter what I've done. Or you can just come up with your own from scratch if you consider that to be a good exercise. Okay? Obviously, the formulation is going to be slightly different because the equation is different and the coefficients and the values are obviously all different. All right, so this is advanced modeling methods. And this will be lecture number 6. So today we are going to formulate the so-called Galerkin method of weighted residuals. Okay, so that's the fourth variation of the method of weighted residuals for us. And remember, what differentiates one from the other is basically the choice of weighting functions, or the weight functions. So in essence, the residual minimization looks like this, is an integral of the residual times different weight functions, and we have been calling this weight functions W omega I, the ith weight function, integrated over omega must be equal to 0. And this is, as you can see, an interior residual minimization. It's the residual over the domain. So the Galerkin formulation, again, it differs from the other ones by the choice of weight functions. In the case of collocation, this was exactly the same residual formulation. We used the Dirac delta function for the weight function. In the case of the subdomain method of weighted residual, we basically use 1 for the weight function and divided the domain into finite volumes, into subdomains. In this case, for the Galerkin formulation, we're going to let the weight functions be equal to phi I, where the phi i's are the same trial functions employed in the approximation of the field variable. i.e., the approximation of the field variable. In this case, we're approximating the temperature.
And so far we've been using just combinations of coefficients, alphas, and trial functions. So in the Galerkin formulations, the weight functions are the same trial functions that employed to approximate the solution. That seems pretty simple, but it leads to a formulation that is very robust and it's actually attained the highest popularity of all numerical techniques, which is the finite element method. So these selection here will make the method of weighted residual the finite element method. And this is the method of choice for solving structural problems, even heat conduction problems. Most of the software packages that you use where these type of things are calculated have a solver that relies on the finite element method formulation. All right. Now in this case, however, it is convenient to employ local support. So just the same way we did it in the case of local supported collocation or the subdomain method, we use local support expansions, file functions. This time, let's select functions that are valid only in the region from xi to xi plus 1. So before, when we did local support, whether it was for collocation or for subdomain, we selected the region of influence to be 3 nodes. Okay, xi minus 1, xi, and xi plus 1. And using 3 nodes leads to a parabola. Okay, 3 nodes, 3 coefficients to determine, that's a quadratic function. If you only have 2 nodes, the best thing that you can do to pass a trial function or expansion function to true points to meet an interpolation exactly is to use a straight line. Okay, so basically we're going to have to use shape functions that are linear. So basically, if this is our domain, and let's say that point xi is here, let's say that point xi plus 1 is here, xi plus 2, and xi minus 1, and that extends to whatever the range of the entire field is, from 0 to L or whatever it is. And let's say that there's a temperature here corresponding to Ti, and there's another temperature here corresponding to Ti plus 1. We're going to call this region here element I, and hence the name finite elements that will result at the end. This is element I minus 1, and this is element I plus 1. So element I is basically the range that spans between node I and node I plus 1. And since we only have 2 nodes, the best we can do is linearly interpolate between those 2 functions, or those 2 values. Second. Okay, so that is the local interpolation of T is Ti plus, trial function 1 of element I plus Ti plus 1 times times trial function 2 of element I, such that x only belongs to the interval between I and I plus 1. Now notice that because there are only two nodes in the local scope, the local region between xi and xi plus 1, the basis functions phi1 of element I and phi2 of element I must be linear. And these are called basis functions because obviously they have to satisfy the basis function property. This one should be 1 when evaluated at xi and 0 when evaluated at xi plus 1. And this one should be 0 when evaluated at xi, and it should be 1 when evaluated at xi plus 1. So if we plot these functions, and let's say again this is xi, this is xi plus 1, this is 1. The first function has to look like this. This will be phi1 of I, and the second function has to look like this. This will be phi2 of I. These are linear, and this is element I. This is the phi1 of I and phi2 of I are the linear shape functions of element I. Ooh. That's not good. All right. So these are very easy to determine, sort of like what we did with the parabolic ones. Okay, we had three shape functions because we had three nodes. This one by inspection. We can see that phi1 has a negative slope, and it would be x minus xi plus 1 divided by xi minus xi plus 1. And this will basically result in 1 over delta x, xi plus 1 minus x. Because this distance here, xi minus xi plus 1, is minus delta x. And similarly, this will be x minus xi divided by xi plus 1 minus xi, which is equal to 1 over delta x, x minus xi. So notice these satisfy the basis function property. That is, phi1 I of x is equal to 1 if x is equal to xi, and 0 if x is equal to xi plus 1. Well, v2 of I is equal to 0 if x is equal to xi, and 1 if x is equal to xi plus 1. So we're basically linearly interpolating the temperature within the two nodes. That allows us to evaluate the value of the approximation of the temperature at any location between xi and xi plus 1, including the nodes xi and xi plus 1. So, again, this is an interpolation. Ti plus 1. Notice, which is exactly what we want, that this is true. All right. So, if we go back to the residual minimization formulation, then basically we have an integral. Now the domain with local scope will only be domain from xi to xi plus 1 of the residual that location times the weight function, which is now the trial function for element I. The x is equal to 0, such that I goes from 1 to n minus 1, and k goes from 1 to 2. Right? So let's look at that residual minimization. Remember, the original formula was the integral over the entire domain, omega, of the full internal residual times the weight functions. We decided that in the Galerkin formulation, the weight functions are going to be the same as the trial functions, but we have two trial functions for each of the elements. Okay, every element goes from node I to node I plus 1. So we're going to integrate this over all these elements, and we're going to integrate it simultaneously for the first shape function and the second shape function. So k takes on the index for the shape function. Okay. Recall the 1D example at hand. So the 1D example that we've been solving so far stays at the differential equation, which makes up the residual, is the second derivative of the temperature plus the temperature itself plus x. And now this is valid only between xi and xi plus 1. Because the approximation has a local scope. It's not valid everywhere. Right? So if we introduce this into this equation, introduce reducing into the minimization formula. We have now the integral from xi to xi plus 1 of the residual, which is all of these, plus a shape function of element I, dx must be equal to 0. And again, this is for I equals 1 through n minus 1 and k equals 1 to 2, because we have two shape functions per element. Had we chosen 3 points for every element, or 3 nodes for every element, then we can do quadratic shape functions on that element. We are at liberty of doing that, and then k will be from 1 to 3, because a quadratic interpolation includes 3 shape functions, as we saw last class. All right. So I'm going to break this up into 3 separate integrals, as we did last time. The first integral, xi to xi plus 1. Second derivative of k I of x dx plus xi to xi plus 1 of t is equal to minus right? So now I'm going to integrate the first one by parts. Integrating first integral by parts. This will result in the first derivative. This is evaluated minus the integral between xi and xi plus 1 of the first derivative times the first derivative of these. And let me fit the rest in here. Negative x v dx. All right, so I just took these and integrated by parts, where this is u and this is dv, right? The integral of u dv is uv minus the integral of v du, right? Now if t is equal to ti times phi 1 plus ti plus 1 times phi 2, then the derivative of t with respect to x is equal to Ti times the derivative of phi 1 with respect to x plus Ti plus 1 times the derivative of phi 2 with respect to x. All right. Now what I'm going to do is I'm going to expand this for phi 1 and phi 2. Right? Remember that this is valid for values of I from 1 to n minus 1. And it's valid for values of k, the index k, from 1 to 2. All right? So I'm going to rewrite this one time as phi 1, let's do dt dx xi plus 1 minus dt dx d phi 1 plus the integral phi 1 I of x minus the integral of x phi 1 I of x dx. And I'm going to repeat this for k equal 2. These are called the element equations. See? So notice that the only difference between equation 1 and 2 is the index k. All right. Now let's look at the first element there, or the first term here. This is the evaluation of this term at xi plus 1 minus the evaluation of this term at the second limit of integration. Okay, this was an integration by parts. So it's basically evaluating this term here minus evaluating this term here. Remember the properties of the shape function? Okay, when this function is evaluated here, you get 0. When this function is evaluated here, you get 1. When this function is evaluated here, you get 1, and when this function is evaluated here, you get 0. Right? So recasting the properties of the basis functions which we wrote in the previous page. So this will be, when evaluated xi plus 1 is 0, so all we have left is minus 1 times dt dx at xi. And I'm going to include here the evaluation of the entire derivative, which is all of these, minus the integral of dt dx, which is, we might not have enough space here, so I'm going to jump to the next line, ti x plus ti plus 1 phi2 by dx, and this multiplies the phi1 by dx, x dx, and then we add plus the integral from xi to xi plus 1 of ti, so it is temperature times phi, of phi1 plus ti plus 1 of phi2 times phi1, and that's equal to minus phi1. That's the first equation. Second equation, when we evaluate this basis function at xi plus 1, we get 1. And we evaluate this function at xi, we get 0. So all we're left with is dt positive dx at xi plus 1 and then minus xi to xi plus 1, and all of these ti. As you can see, this formulation is a little bit more complex, but at the end of the day, we're just going to have coefficients multiplying a matrix coefficient, multiplying a vector to find the alphas or the nodal temperatures. And this will be V2 dx plus xi to xi plus 1 of ti v1 plus ti plus 1 v2 times v2 is equal to minus v2. Okay, so we have two equations, one for each of the weight functions, each of the trial functions. All right, so I'm going to just rewrite this, and I'm going to combine everything that multiplies ti and everything that multiplies ti plus 1 on both of these equations, and everything else I'm going to send to the right-hand side. So, since ti and ti plus 1 are not functions of x, these are just nodal values, I can take them out of the integral. So here we have, I'm going to go to the next page because I'm going to have an equation that's probably going to look as large as this one. So I am going to have ti, I multiply everything by minus 1, and ti, that multiplies the integral from xi to xi plus 1, and notice ti is multiplying on this first equation the derivative of phi1 and the derivative of phi1, so derivative of phi1 times the derivative of phi1. Remember, phi1 is defined, so the derivative is also defined. And ti is also multiplying in this equation phi1 and phi1. And since we multiply everything by minus 1, we get phi1, phi1 dx. And then we have ti plus 1, which multiplies an integral from, and ti plus 1, as you can see, multiplies d phi 2, or d phi 1 times d phi 2. and multiplies phi1 and phi2. Negative phi1, phi2 dx. And that's equal to now we multiply everything times -1, so this will be integral xi plus 1 of x times phi1 dx, and then this one will result in negative dt dx at xi. I left that on the right hand side. So that's the first of these two equations. And the second of these two equations looks like this. Ti multiplies an integral and Ti multiplies d phi2 d phi1 and it multiplies phi2 and phi1. And conversely, Ti plus 1 multiplies d phi2 d phi2 and it multiplies phi2 phi2. And this is equal to the integral this is plus all right.
Professor, you said the top one was the first integral?
The top equation is the same equation here. The same equation, I just rearranged it. I just took Ti out of the integral and just multiplied through, and took Ti out of the integral and multiplied through, and then just combined. And I took Ti plus 1 of them. So this first equation right here is equivalent to this first equation. This first equation is equivalent. I just move the terms and multiply times -1. Now the point is that we have, this is a number. Whatever these are, we know what they are. We can integrate them. These are just linear functions. The derivative of linear functions are constant, right? So this is a constant minus a quadratic function, linear times linear. We can integrate a quadratic function over x by hand, or we can have the computer integrate it for us. And at the end of the day, this is just a number. This is a coefficient multiplying Ti times a coefficient multiplying Ti plus 1. This is a coefficient multiplying Ti, and this is a coefficient multiplying Ti plus 1. This right here is a number. And this right here is related to the flux at the location of the node I, and this is related to the flux at the location of the node II plus 1. So basically, these results in a system that looks like this: K11I, K12I, K21I, K22I, that multiplies Ti and Ti plus 1, and this is F1, F2, plus, and if we call this the flux, or Q, this is the output algebraic form of the finite element method, FEM, equations for element EI. In finite element language, this is called a stiffness matrix. And the name stiffness comes from the fact that, well, finite element methods was originally formulated for structures problems, solid mechanics, and this is basically related to the stiffness of the system. This is the vector of displacements or deformations at the nodes of an element instead of temperatures. We're just formulating it here for heat conduction. This is the forcing term, and this is related to the derivative of the field variable, in this case, the derivative of the temperature. So the elements K and M of element I are simply the integral from xi to xi plus 1 of d phi n dx d phi m dx minus phi n of x phi m of x dx. And this is called, again, the stiffness matrix. Now where to write it. F and I is equal to the integral of x dx, and qi is related to t, or dt dx at xi, while qi plus 1, in this case, is dt dx at xi plus 1. So these are the related to flux, nodal fluxes. And remember that the flux is not just simply the TDX. There's usually a minus K in front, but this is it's related. That's why I say it's related, not directly to fluxes. This is the forcing term, and this is the stiffness matrix. So each element has two equations attached to it because each element has two shape functions. If we had used parabolic shape functions, then each element will have three of these. So what we need to do is use these equations to assemble nodal equations. So if we look at
Slide it down just a touch.
Sure.
Just to the KCM.
Yeah, there you go. Now look at elements EI minus 1 and EI. So we have a node here, I, we have the node I plus 1, and we have the node I minus 1. So this would be element EI, and this would be element EI minus 1. This node has a corresponding Ti and a corresponding Qi. This node has a corresponding Ti plus 1 and Qi plus 1. And this node has a corresponding, whatever it is, Ti minus 1 and Qi minus 1. So if we write the FEM equations, these equations that we wrote up there, for this element, next to the equations for this element, it would look like this. So we have K11, K12, K21, K22. This is a matrix. This will multiply Ti minus 1 and Ti. This will be F1, I minus 1, F2, I minus 1. And this will be minus Qi minus 1. And this will be Qi. And this is for element I minus 1. And then for element I, we'll have K11, K12, K21, K22, Ti, Ti plus 1, whatever these forcing terms are, just those integrals. And sorry, this was plus minus Qi plus 1. And this is for element I. All right, so what I'm going to do is realize the fact that, see, these are two equations for element I minus 1. This is two equations for element 1. Notice that the second equation of element I minus 1 has Qi. And the first equation of element Ei, which is these 2 times these 2, equals to this plus this, has also Qi. So those two are in common. So we can add those two equations, eliminate the Q. We don't want the Q to participate in anywhere here, right? We want to formulate an algebraic system where the unknowns are just the temperatures. So to formulate the nodal FEM equations, use the first, you can do first equation of EI and the second equation of EI minus 1. So this will result in the following. The second equation of EI minus 1 is K21 I minus 1 times Ti minus 1 plus K22 I minus 1 times Ti is equal to F2 I minus 1 plus Qi. Everybody agrees with that? The second equation here, this one times this one times this one is equal to this one plus this one. And the first equation of element EI is this one times this one plus this one times this one. It's equal to this one plus this one. So that would be K11 times Ti plus K12 I times Ti plus 1 is equal to F1 of element I minus Qi. This is a minus, this is a plus. Adding and recognize that the derivative Qi is continuous. So we're basically saying that whatever interpolation we use, we want the slope to be continuous. We want the slope of that interpolation at every node to be the same. So the derivative of the temperature, whatever that is, an element, and the second node of element EI, or element I minus 1, has to correspond to the slope of the field variable on the first node of element I. So these two will cancel out, And this will result in K21 I minus 1 times Ti minus 1 times, or I'm sorry, plus K22 I minus 1 plus K11 I times Ti plus K12 I Ti plus 1 is equal to F2 I minus 1 plus F1 I minus 1. And these are the nodal FEM equations for field variable T. Notice that valid for I going from 2 to n minus 1. This is not valid at the end nodes because it uses a temperature one node to the left and it uses one temperature one node to the right. So we cannot evaluate this at I equal 1 because it will actually refer to a temperature that doesn't exist, and we cannot evaluate this at I equal n because then it will refer to a temperature past the last node that doesn't exist. So at the end of the day, we have sort of the same thing that we had before, the same type of equation where we relate the temperature with its neighbors, all values of n, and it's just coefficients multiplying temperatures, coefficient multiplying temperatures. It's just that the coefficients are calculated differently in the FEM formulation than they are in the finite volume formulation than they are in the finite differencing formulation. But at the end, the algorithm is identical. We can actually use the same code and just alter the way we calculate the coefficients. Obviously, these coefficients are a little bit more involved because they require integration. Before, those coefficients we just did by hand. We can do this ones by hand because these shape functions are linear, but so essentially the algorithm will look like at I equal 1, xi equals x1, temperature I is equal to the temperature, the imposed temperature, at I equals 2 to n minus 1, xi equals x2 to xn minus 1. Then we have these coefficients k21, I minus 1, plus k22, I minus 1, plus k11. Yeah, I am just repeating this equation. It's equal to F2 plus, oops, I'm sorry, I made a mistake here. This would be F1 of I. Just F1 of I. All right, and at the last node, since we know the temperature, then Ti is equal to whatever value that temperature is imposed with. All right. So now, what if the flux was imposed on the first node? Or if a flux was imposed on the last node? Then we have to use the nodal equation, which the Q doesn't cancel out or remains. So if the flux is equal to minus k dt dx times the normal is imposed at any of the n nodes. That would be x1 or xn, can be at both. Then use the FEM equations. That state that at I equal 1, xi is equal to xn, sorry, xi is equal to x1, then we'll have k11 1 t1 plus k12 1 t2 is equal to f1 1 minus q1. And at I equal n, xi is equal to xn, then we have k21 n minus 1 tn minus 1 plus k22 of n minus 1 tn is equal to f2 of n minus 1 plus qn. But recall that these q's that we use in the formulation are just the derivatives. They're not multiplied by k, they're not multiplied by the normal vector. Recall that in the FEM formulation above, this guy and this guy right here, the Q terms are defined as just the derivative. That is, Q1 is equal to the t dx at x1, while Qn is equal to the t dx at xn. While actually the heat flux Q minus k dt dx times the normal vector will be at x equals 0, then Q, which is equal to minus k dt dx times the normal vector, which is minus 1, is some Q0, and therefore the t dx is equal to Q0 over k, while at x equals L, Q is equal to k dt dx, and on the right hand side of the domain, the normal vector points to the right, so it's positive 1, and that's if it imposes a QL, then the t dx, would be at x equals 0, and this will be at x equal L, is equal to minus QL over k. So I'll just take altering the first equation or the last equation, or both if you have fluxes on both sides. All right, let me know when you're done so I can show you that the MathCAD spreadsheet doesn't actually look very different from the other ones. It's just that those coefficients are integrated. And again, what we're going to do on Thursday is a matter of exercising this. I'm going to take the FDM, the FBM, and the FEM formulation and do it again using MATLAB. Okay? So you have available all the MathCAD codes and all the MATLAB codes. So you can actually do project 1 by altering either the MathCAD code or the MATLAB, whatever you feel more comfortable, or if you want to write your own in C or Java or Mathematica, Maple, whatever you want to do, just do it that way. And I've included in I'll show you what the project statement looks like. Are you ready?
Just one moment. Do it in Excel spreadsheet.
You can do it in Excel too. Yeah, that's doable. You can do it in Visual Basic. Write a graphical
Once you
user
get the
interface.
initial, you have to have like 1,000 sheets.
Well, this is a 1D. Imagine in 3D,
Oh,
the elements are triangular, so you have 3 shape functions per element. It becomes all more convoluted. I had a student at UCF who did an Excel code for a 2D finite element. Solve it. No, Excel, pure Excel, iterative. So it's kind of an overkill because it takes a lot more effort to do it in Excel, but you can do it.
Yeah, heat transfer, Professor Boecher had us do, had us do the Excel two-dimensional heat transfer. It wasn't bad.
In Excel?
Yeah, you wrote the equation once and then kind of just like click dragged it out, so it wasn't a terrible problem.
Professor, to get access to MathCAD, you have to go to your lab.
Yeah, it's only in my lab, but MATLAB is on every computer account. I just like MathCAD for teaching because it's very visual. Okay, whatever I want to do, I can alter it and parametrically compute, and then I can show the results and move the plots. MATLAB is closer to a high-level programming language. It's closer to a Fortran or C or C++. It's not there yet. There's a lot of overhead in between. There's a lot of interpreting, and hence it's orders of magnitude slower than a compiler. All right, so we have the same 1D problem, whose solution is in terms of cosines and sines, and that x that satisfies the governing equation and boundary condition and results in this particular temperature distribution. Okay? Now we're going to do this with finite elements. We're going to establish the origin at 1, and notice that everything is identical. I'm deciding that I'm going to have 11 points that cover the domain from 0 to L, so the spacing is L divided by n minus 1, and the index goes from 1 to n, and every grid point, which I call xi, and it's also indexed by I, is I minus 1 times delta x. So xi would just be points at 0, 0.1, 0.2, all the way to 1. All right, so I am zeroing the coefficient matrix A. These are the shape functions. Shape function 1, that's the one with the negative slope, and shape function 2 is the one with the positive slope. Okay, they are basis functions. One goes to 1 at its own node and goes to 0 at the other node, and vice versa. And the derivative of these is pretty simple. It's minus 1 over delta x, and the derivative of the other one is very simple. It's 1 over delta x. So basically, the coefficients k11, k22, k12, so on and so forth, which is k11 will be this one times this one minus this one times this one integrated between node I and node I plus 1. And I let MathCAD do that for me. I can do it manually because this will be just a matter, this is a constant, this is 2 linear functions which will make a quadratic function. I can very easily integrate that. It will be a cubic function, cubic polynomial. Evaluate the cubic polynomial here, and I'll just end up with a number. Okay, basically a number that depends on delta x and so on. I just don't want to do it. Oh,
When you took your derivative of phi and phi2, what did you take it with respect to x?
with respect to x.
So you, not xi, so you just have -1 over
Yeah, if you take it with respect to x, you get negative.
-1.
Yeah, xi is a constant.
Okay, and for the second one as well, it's just x.
With respect to x, so you get positive 1 over delta x. All right, So these are the coefficients on the FEM formulation. These are the elements of the 4x4 stiffness matrix, essentially.
You're multiplying the equation that we wrote down earlier of the matrix.
Those are the elements of the 2x2 matrix. Little square matrix 2x2, element 1, element 2, element 3, element 4. 1, 2, 3, 4. Well, and these are going to be different for each node. Okay? This also allows for the possibility of the nodes not being equally spaced. Okay? So then every one of these integrals will result in a different number. But if you look closely, these shape functions are all the same and these derivatives are all the same. Okay? So phi1 for element 3 is the same as phi1 for element 4, and so on and so forth. So basically, the coefficients of that stiffness matrix are the same for every element. Okay? The 4 coefficients might be different from each other, but that matrix is the same on every element because the shape functions and its derivatives are the same. And the location of the nodes are the same. The forcing term, or the 2 forcing terms, right here, that corresponds exactly what we just wrote. And now we just simply assemble the nodal equations. The first element of the matrix A, this is the global nodal equation that encompasses all the grid points. Row number 1 basically says that the first temperature, element 1, 1, is equal to 1. That means temperature, the first temperature in the array is equal to the imposed value T0. All the other elements from row 2 to row n-1, this is exactly the same thing as we wrote on the paper. Okay? This is what multiplies Ti minus 1, this is what multiplies Ti, and this is what multiplies Ti plus 1. And on the right hand side we have the forcing term. So this particular 3 lines are identical from finite differencing, finite volumes, just that the coefficients are different. And at the end we end up with the same. A global matrix A that is kind of sparse, right? Because if we print this matrix, if we evaluate this matrix A, it's going to be an 11 by 11 matrix. But notice, well, the first row is only a 1 and a bunch of zeros, but then after that it's just a tridiagonal matrix. Okay, because every nodal temperature is only influenced by its own 2 neighbors. Right? There's no global influence here. And notice that all the coefficients are the same. See, this repeats and repeats and repeats. And it repeats because all the shape functions are the same, the nodal distributions are all the same, this is all equidistant. Had this been an irregular geometry, like what would happen in 2D if you had an irregular geometry, and every element is different in shape and size, all of these, every single element is a triangle of different shape and size, then basically this coefficients will be completely different. Alright, so the solution TFEM is just simply a to the minus 1 times b. And now what I'm going to do is plot it against the exact solution. And again, qualitatively, it's not much to tell. It looks very good. Same thing as FDM and same thing as FEM. I'm sorry, FVM. But the real test is when you calculate this residual or the error, which is basically a scale percentage error. And if you compare the error for 11 grid points with the 2 other techniques, this one is an order of magnitude better. It is a full order of magnitude better. Not only that, but if you were to increase this number and to increase this number n by, let's say, 2 orders of magnitude, make it 1,000. Obviously, this is going to be a lot slower. Just did it. But if you look at the residual of the error, it's 1/1000 of a percent. It's tiny, tiny. The residual doesn't accumulate, round-off doesn't propagate, and you can just increase. Obviously not boundless, you cannot make it 0, you cannot make the spacing 0 because then you'll have round-off, but on that particular spacing it's not going to propagate, like in global collocation. So this results in a more accurate approximation, more stable, more robust approximation of the solution. And you'll get to compare that when you do when you do the homework. So if we go to, let me see, I already solved it. All right. So project number 1 looks like this. So consider the one-dimensional steady heat conduction problem in a non-homogeneous energy generating medium where the temperature field is governed by the following second-order linear or linear differential equation. Same thing that we're doing. It's just that the equation looks different. Okay, instead of t, we have dt dx. Well, we have a k and we have a c. Instead of t, we have dt dx. And instead of x, we have g cosine of beta x. And the boundary conditions are slightly different. On the left, you have a flux, and on the right, you have a temperature. The one on the right is identical. Okay, so all you have to do is modify how you evaluate the residual on this, and how you evaluate the boundary condition on the left. I'm giving you the exact solution, which took me a little while to derive, but I tested it and it works. And I did it like that on purpose because I wanted something that was kind of nasty. I wanted a function that actually oscillated a couple times, that had decay, and they had a couple things that we can test really how these methods work. And these methods are able, with just local shape functions, of capturing such behavior. All right? So are these coefficients that are not in the equations, like alpha and gamma, are defined like this. Okay?
So we have to isolate those variables to solve for alpha and for gamma.
What's that? No, alpha is just c over k. And I give you c and I give you k. And gamma is 1 over alpha squared and beta squared, and I give you beta. So from the equation, from the governing equation, you'll know, well, k is related to the conductivity, okay? Well, it is a conductivity in this equation. C is sort of related to the non-homogeneity of the medium. If the medium in which this conduction is taking place is not homogeneous, not uniform, C is kind of a variable that correlates that. C is kind of associated with the cross-section change, and it's associated with K, and the functionally graded material, and so on. G is associated with the generation of the medium, so there's internal energy generation. So I'll give you these 3 values, K, C, and G. I'll also give you L, obviously. I'll give you the Q at 0, and I'll give you TL at 0. Okay, it's just that the exact solution would have looked a lot longer had I actually put in the C's and the K's and everything else in there. So I just had space for one line. So I defined this alpha and this gamma. So if you consider the case where L is equal to 1, K is equal to 1, C is equal to 10, G is equal to 1000, and beta is 4 pi over L, the flux on the left is minus 100, that means heating. Okay, remember the flux is usually defined as, it is defined in the direction of the normal. The normal points out, so by saying that the flux is negative means that the heat is going in to the domain. And that the temperature on the right is equal to 100. Then the temperature will look like this. You can test that, you can put that function in MathCAD and that temperature will look like this. So I wanted a weird looking temperature to actually get some errors here. Something that can be appreciable qualitatively and obviously quantitatively. So what you're going to do is you are going to approximate the solution of the provided boundary value problem using the following 3 variations of the method of weighted residuals. You're going to use FDM, you're going to use FVM, and you're going to use FEM. Okay, that's it. And you're going to do that using n equal 11, n equal 101, and n equal 1001, so 3 orders of magnitude change. For each of the 3, so you're going to do this 9 times basically. Well, not 9 codes, you're going to write the same code and you're going to run it 3 times. Report the plots comparing the numerical approximation to the exact solution as well as the value of the corresponding approximation residual for the 3 discretization levels. So it's that. So we're going to define the residual like this. The residual for the numerical method that you're using, whether it's FDM, FBM, or FEM, will be like this, where the subscript num indicates the method employed, either FDM, FBM, and FEM. Therefore, you are to report 9 of these residuals, right? 1 for each method, 3 for each method. You may alter the MathCAD or MATLAB codes provided in class, or program your own code using any mathematical spreadsheet, MathCAD, Mathematica, Maple, Excel, or high-level programming language, MATLAB, Fortran, C++, whatever you want. Your report must include these cover pages signed with your name, the plots, the residuals, and your code listings. All right? That's all. And it's due on Thursday of next week. So you have everything in hand to do it. Again, I'm going to do it in MATLAB on Thursday, which should actually give you another alternative to your solution. Any questions?
Well, I think I already know the answer, but this is not helping each other at all. There's no like, you can't like meet
Like,
and
could we work
discuss
with
it.
a buddy and then each do their own work?
Yeah, you can talk to each other. I'm obviously not going to prepare each. There's got to be original individual work.
Yeah.
All right. Everyone submits its own report with its own individual touch to it. Okay. I don't want copies of reports or copies of code listings. Okay. Make an effort to alter the code and understand it individually. Okay. If you run into trouble, obviously you can ask me or ask one of your classmates. Okay. All right. So that's it. I'll see you Thursday.